All right, so the next we're going to look at electric field. So electric field is not exactly the same as electric force. And this is something that I've seen students sometimes struggle with. So we have electric force, which is basically interaction between two charged particles. If you have two charged particles, they exert force on one another if they have a finite distance. So let's say you have here charge one, you bring another charge two, and if they have a finite distance, then they exert force on one another. That means you need two charges, let's say at least, in terms of um, looking at their interaction and calculating the force using Coulomb's law. Electric field is different. And the way we can think of like electric field is this. So let's say there's um, considering the space here below that line. So there's right now nothing there. There are no charged particles, nothing. So in a way, it's vacuum, empty space. But then what we do, we bring a charge. So let's say we bring a charge like that. Okay, do a little bit straight line like this. So let's say we bring a charge. Now this is just a single charge. Um, Again, could be just a point particle, could be a sphere, right? But the idea here is as soon as we bring this charge over here, all the space around it is now changed in terms of like the properties of the space itself is modified because of the presence of this source charge, because this is the source of that modification, alteration of this space itself. And we can find then or see the effect of that whenever we, let's say, bring some kind of test particle. All right, so the idea here is this. Now, any point around this charge that I look at before this charge, it would have been just basically nothing, empty space. But now I can find and calculate some kind of effect, property. They're what we call fields now, electric fields. And the electric field basically, fill the entire region. And electric field is a vector quantity. That means it has a magnitude and direction. So we can kind of represent it with an arrow, for example. So let's say if I consider this point here over here, right? Then what I will do here is look at the distance of that point P from this, source charge, and then find the electric field strength in terms of magnitude, right? And the direction. Now, the direction is relatively straightforward to at least, use an arrow to represent. If it's a positive charge, if the source charge here is positive, then the electric field generally points radially away from the charge. So that this will be electric field, and we use capital E for that. So then this will be an electric field. So it's radially away. That means, for example, if this is the point P prime, right, point of interest, then I draw the line toward the center of that source charge or toward the source charge, right? And then the electric field again will be then radially, right, radially away. So at any point, it will be radially away. I should actually, make this a little bit longer. And the reason here is because this point P prime is closer to the charge than P. So then electric field here will be stronger. Closer you are to the charge, stronger this effect. All right. That means this entire region is basically filled with this electric fields. Now, there's a nice simulation that I want to, show you in terms of how we have empty space and we plug in that and then you see the fields. It's not a nice simulation. I want to show you so you guys have a nice visual understanding of this. All right. So let's say we have this simulation over here. So we consider, empty space, right? Think like this entire region is like empty space. And then I can bring either a positive or a negative charge. So this is going to be then the source charge. Okay, so this is going to be source charge because this will be the source of the, let's say electric fields, all those fields, right, generated in this region. Now, let's say what I will do here is I will just, take here 1 nanocoulomb of charge and place it technically anywhere. As soon as I place it somewhere here, then you should be able to see then all those fields that it generates. There you go. And you can see, right, that means the entire region now affected by this, by the presence of this source charge. That means I can, at any point, right, doesn't matter where it is. So you can see, right, I can look at in terms of this point over here, P, this point over there, P prime, this point over here, let's say P double prime. they all will be affected by the presence of this, electric, sorry, source charge. And all the electric field, right? You can see in this entire region represented by those arrows. So you can see, right, if I draw a line to P, see, this is along that, the same one over here, right? Will be radially away like that. So for this one over here, it will be radially away like that. And the same thing here. If I draw this one in terms of here, say it radially away. That means all the electric fields going to be pointing radially away from the positive source charge. And also closer they are to the, let's say, to the source charge, stronger the field, stronger the effect. Okay. Now, what happens if we have a negative charge? Well, let's see what happens. So I'm going to reset. I'm going to clean this board. Now let's look at now if I put a negative one. All right, so here's a negative. All right, so same effect. It right away affects the entire space. But this time the effect itself is basically electric field pointing radially toward the charge. I guess that's one thing you can see the difference, right? It is pointing toward the charge rather than away from the charge. Um, but in a way, one of the things we can see here is still the entire region filled by these electric fields. And obviously, right now, this is a, uh, let's say, the simulated, the visual of the electric fields. We don't really see the electric fields, but we do feel the effect of that, and we can um, verify that by basically testing. So, so that's kind of, let's say, what we have. Thing like this. So this entire region now is affected by the presence of this source charge. Now, the idea here is then, if I want to verify, right? So if I want to verify, I can think of it like this. So let's say I don't know if there's a source charge. Let's say I don't see the source charge. Even let's say if the source charge is a little bit further away, as long as let's say there's a source charge in the vicinity of this region, this region will be affected by that. Now, how do I know that? Like, how do I test that? Well, I can bring a test particle. Okay, I can bring a test particle and I can test that. But before that, I want to give you, like, let's say, analogy. And I can just basically use this space over here to do that analogy. So let's imagine, remember, I showed you how Coulomb's law kind of very similar to the gravitational law, right? In terms of the proportionality, what is it, depends on, in terms of inverse square law proportionality and all of those things. So let's imagine this. Now we have some kind of, object that has mass. Let's say it's Earth. So let's say here's Earth. Okay. Let's say this is Earth. And obviously what I'm looking at here is giving you analogy. So Earth affects things that have mass because it also has mass. So this is mass of Earth. Okay. Now, all the region now around Earth will be affected because of the presence of Earth. Okay. Again, because Earth is then going to be the source of any type of gravitational effect. Again, because it's much bigger than anything on its surface. So let's say this is Earth, it has a large mass, and it affects all the space around it. And that's actually exactly what happens as well. That means that all the space around Earth is affected by the size of Earth itself. And the Earth creates fields that are not electric fields that it creates gravitational fields. So gravitational fields are basically this, fields that we cannot see, right? They're invisible fields that are always, just like electric field can be represented by an arrow, can be, can have a magnitude and the direction. And one thing we have here, they're all similar to, let's say, remember for the negative point charge I just showed you, right? Electric field pointing toward the, let's say, toward the charge. So it's kind of similar. This electric field, the gravitational field that it creates, it's always pointing toward Earth. Okay, always pointing toward Earth. Now, these fields, again, we cannot see them, but we can detect the presence of the gravitational field, because what I can do here is this. If I bring another object that has mass call it a test mass. So let's say another object, put it here that has mass. Then I can test to see if there's a, you know, effect or not. Because if this test object, let me put like M naught, if this test object, if I place it there, it will right away recognize that there is a field and it will be affected by that field. So it will right away be affected by the gravitational field of Earth. Now, what happens here when it's affected by Earth? Let's say we can say then it's pushed or pulled by that effect. That means that, this gravitational field then exert force on this mass, the test mass. Now, one of the things that we will have here is then the force that this test particle will experience will be attractive toward Earth, and we just call it gravitational force, right? That's why if you take right now a marker or a pencil or something like that right next to you, hold it and let go, it's going to fall down. Why? Because all this region in your room is right now affected by presence of Earth. And all that region is filled with the gravitational fields or gravitational effect of Earth. The way you would recognize or verify that, just take anything that has mass, hold it, let go. It will right away recognize that there's a gravitational field there. It will be then pushed or pulled by that field, and in this case, right, this mass, the test mass object will be pushed, in this case attracted right toward Earth. And then what we can do here, we can calculate the effect, because that effect is always going to be, we will able to calculate that in terms of the, let's say, the force let's say the force exerted on the test particle or test mass. So let's say then the force, in this case, let's say gravitational force, right? So basically the force that this particle experiences per, you know, mass of that particle, so force per mass, is then what this gravitational effect is. Hopefully you can see, right? If I divide gravitational force by, mass, I'm going to get G. And G here is what, kind of equivalent to the electric field. G was the gravitational effect of Earth, right? Any test objects, right? To be a rock or an arrow or anything like that, right? Will be affected by that. That means this equation tells you that if you take the force of the field that field exerts divided by the test mass, you get then the effect itself, which is the gravitational effect, right? Gravitational acceleration. So this is very similar to that. Again, take any object with mass and verify that there's a gravitational field. Because if there is no gravitational field, right? If you do that in vacuum, there's not going to be there. There's, let's say if you go into space, there are no other planets or stars, anything around you. So you're holding something, you let go, it's just going to sit there because there are no fields over there. Or it's so small that, it's not going to be affected by that. So that's kind of like the idea. That means if I come back over here and I have this charge, let's say if I put this charge here, you can write, you technically will not be able to see those. So let's say it's something like that, right? But now all that space is filled with electric fields. Okay. So kind of like this. Now, then one thing we can do, by the way, this is kind of like the shading represents the magnitude. So brighter it is, stronger it is, fainter it is, weaker it is, right? So let's say in this particular case, it's nicely represents, the magnitude is stronger, closer to the charge. Now, one thing we can do here is this. Again, how do I know, let's say, if there was no, let's say if I couldn't see electric field, how would I know there's electric field? Well, the same thing as that we did for the mass. I can take and bring a charge, but this is a test charge. So think like this. So this is my source charge. Now this is going to be my test charge. Then if I bring this test charge and it is pushed or pulled, that means there's electric field. Because if I bring that test charge, see, this test charge is going to be sitting in a region where there's already an electric field. And then there's going to be a force acting on it, right? So there's going to be a force acting on this test charge, and this is going to be electric force. And this is force per unit charge, kind of similar to the gravitational force per unit mass. Remember, charge is intrinsic property of the charged particle. Mass is the intrinsic property of the object that is affected by the gravitational force, right? So this ratio force per mass is equivalent to the ratio force per charge, which then we define to be then the electric field. Okay. That's why as soon as I place that test particle over there, there's going to be force acting on it. And this force, if I rearrange this equation, right? So you can see, right, that force, electric force is equals to test particle times then the electric field that is already present over there. So then this is, I can see that as soon as I put it there and I let go, there's going to be force acting on it. What is the magnitude of the force? It's charge times the electric field. Just like what was the gravitational force? It's mass times the effect. So charge times the effect, mass times the effect, and that's kind of like where you hopefully can see the analogy between gravitational and electric interactions. All right. So hopefully, this would help you then if we go back to our slide. Then one thing we can see here is this. So let's say if I have this source charge, then all this region is filled with electric fields. And I don't really see that, but I can test it by bringing a test charge. So we bring a test charge, and because this region at that point P, right, there was electric field over there, there's going to be electric force acting on it, because then we can say that as soon as the test charge feels the presence of the electric field, it is being pushed or pulled. Or you can say that as soon as you place it there and there's electric field, it's going to right away exert force on this test charge. Okay, so um, so you can see, right, kind of like explain this. The test particle is used to detect the existence of the field. It is also used to evaluate the strength of the field, as I mentioned, right? So the equation is the force that we can technically, measure that experiences divided by the test charge, let's say particles test charge, right? We can find the electric field. All right. So the electric field is said to exist in the region of space around the charged object. This charged object is then the source particle. That means that the sphere that we had. So then when another charged object, the test charge, enters the field, this electric field, an electric force acts on it. And here's the equation. If you do the force per unit charge, that's defined to be an electric field. So that means the units are newtons per coulomb. Force in newtons, charge in coulombs, electric field basically Newton per coulomb. All right. Now, what it means here is that this electric field will exert force on a test particle. And electric field magnitude and direction doesn't depend at all on the test particle. It only depends on Earth. So that's why, for example, when you have, let's say, Earth and its effect, right? It's not different if you have a one object compared to another one, right? All of the objects have exactly same effect acting on them. You holding something, you let go, they all fall straight down. You don't have to, like, one object goes up, the other one goes to the left, to the right. I'm talking about like a dropping, right, straight down. So just let go and then it falls down. So the same thing here. This electric field is the property of the source charge. It has nothing to do with the test charge. So that's why, let's say, you can see that in the equation of the electric field, and this is like, let's say, one of the equations of the electric field. There's another one where you can calculate, from the information of the test charge, source charge itself. This is, let's say, if you bring a test charge of the 5 nanocoulomb and it experiences, 10 newtons of force, we can calculate what was the electric field. All right, so again, important thing here is the electric field produced by some charge, or also can be multiple source charges or charge distribution, but has nothing to do with the test charge. So the existence of electric field is a property of the source charge. So the presence of the test charge is not necessary for the field to exist. That means, as I said, right? So if you go and look at that simulation, so if I go back over here, see, let's say once I place the source charge there, the electric field is there, regardless if I have a test charge or not. This region filled with electric field, even though if there's no test charge at all. I can look at any point around this, let's say, source charge. Here's a point, here's point, let's say here's another point, and I can find then the electric field, regardless if I have a test charge or not. If I bring a test charge, electric field will not be different. It's not going to change at all. But what will happen is that this field then will push or pull the test charge. All right, let's go back. So that's why rearranging that equation, you have Fe equals Q times E. Again, similar to gravitational force is mass times G, right? So the intrinsic property times the effect. That means you can say that you have the electric field because of the source charge. Then you bring a test charge. This is a test charge. And then you can calculate how much force the test charge is going to experience because of that electric field that is present over there. So, well, I can actually show you over here, right? Well, maybe here. So think like this. Remember that equation for the Coulomb law? KQ times, let's say that means if you talk about, let's say here's a source charge, we can just use it as Q. And let's say here's a test charge, Q naught. So if I bring it at some point P, think like this. Because of this was the source charge, that point P, there was already an electric field, right? Then I bring some kind of test charge. Well, the force is the Coulomb's force. K times Q naught over R squared times R hat, the unit vector. Then if I take that force, think like this, right? If I then divide it by the test charge, like, like that this equation suggests, right? If I take it and divide by the source charge, that means I'm dividing this by divided by the test charge. See, this information about test charge completely cancels out. That's why electric field has nothing to do with the test charge. So it's force per unit test charge. Both force has information about test charge, then you divide it with the test charge, Q naught cancels out. And then you have equation where it's KQ over R squared, then times the unit vector R hat. And this is the equation for the electric field. That means I don't need any type of test charge technically to calculate what is the strength of the electric field over there. If it's a positive test charge, direction is radially away, and the magnitude given as K times the magnitude of the source charge divided by the distance square to that point P. And then I can calculate the strength of the electric field. Okay. So that's kind of, what we have in terms of the strength of the electric field. What if there's, here's one source charge, and let's say I have point P over here, then I can say, all right, so there's a electric field radially away from that. Here's electric field. But then this is one of the source charges, so it becomes electric field 1. Maybe I have another one, but this is a negative source charge. Well, that means that point P now will be affected by both of those source charges. And there's going to be also electric field due to this Q2. Let's say in which direction? Well, Q2 is negative, so this electric field will be radially towards this. So then at this point P, what I need to do then calculate the net electric field, because electric field is a vector. This equation tells you that if you have multiple, source charges, that you need to just, find the net electric field. Well, easily I can do the graphical way of determining the direction. You can see, right, parallelogram method then allows me to see that electric field will actually be here. That means at that point, there is the electric field in that direction because of I have Q1 and Q2, two different charges. At that point, electric field will be actually at that pointing in that direction. Magnitude, then I need to add those two vectors as those two electric field as vectors to get then the magnitude, which we'll do. You guys can see in examples. Okay. All right. Again, sort of like let's say think like this. What I have here is let's start with this one actually. So I have a source charge, and at some point P around that source charge, right, I can calculate the electric field. Now, when I bring a test charge at that point P now, there's already an electric field over there. And then we mentioned, right, there's going to be electric force. Equation for the electric force is Q times E, but it's a vector, so Q times vector E. And here's the thing. If Q naught, so this is Q naught. If Q naught is positive, that means we're dealing a positive test charge. You can see, right? Look at the direction of electric field. Now look at the direction of the electric force. So if Q naught is positive, force and electric field have the same direction, both radially away. That means in in the case where the test charge is positive, or the matches the charge of the a source charge. Well, let's say it's positive. Let's do it in terms of that. If the test charge is positive, it will have the same direction as electric field. Well, which makes sense, right? If this is positive charge, this is positive charge, is going to be repulsive, and the force on the test charge will be in that direction. But we can also deduce it from this. Because it's a positive test charge, the force acting on it has the same direction as electric field. Well, what if this was a negative, test charge? What if this was a negative test charge? Well, going back to this equation, then I have Fe equals Q times E. Well, think like this. If the Q naught here was negative, then I put a negative over there. Then it says that Fe equals negative of E, which means now the direction for the force that will be acting would have been then in opposite direction. So force would have been in this direction, which should also make sense, right? If this is a negative charge, it will be then attracted toward the positive source charge rather than being repelled by that. But this is what we have. If the test charge is negative, the force acting on it would be in the opposite direction of the electric field. Okay. So that means, let's say if Q naught is negative, so then the electric field and force have opposite direction. Okay. Here again, so if Q is negative, the force on the test charge Q naught is directed toward Q. Okay. So this is because, for example, the electric field would have been in this direction. The electric field would have been in this direction. And if this is a positive test charge, force would be in the same direction as electric field. Say electric field is in this direction. If I bring a positive test charge is going to have a force acting on it in the direction of the electric field. And if it's a negative test charge, is in the opposite direction of electric field. All right, so we can look at some examples here. A housefly walking across a clean surface can accumulate a significant positive or negative charge. In one experiment, the largest positive charge observed was plus 73 picocoulomb. Remember, we still talk about like housefly. A typical housefly has a mass of 12 milligram. What magnitude and direction of an electric field would be necessary to levitate a housefly with the maximum charge? Could such a field exist in air? Well, let's see what we have. Let's say I'm going to make my housefly as a particle like this. Okay. And since we're given its mass, we can assume that there is a gravitational force. Okay, there's a gravitational force. Because usually gravitational force is very small compared to the electric force, unless the charge itself is very, very tiny. So then maybe the gravitational force can be comparable, and that's what we have, right? When it says levitate, that means there is a force acting on it, right? So first of all, let's say we can assume that there's an electric field, which then exerts force on the housefly. But in order for it to levitate, then this force obviously has to be in the opposite direction. So it has to be in this direction. So then this is electric force. Okay. That means levitate means that it just not flying up or down, left or right. It's just basically, sort of like in equilibrium, which means then Fe is equals to Fg. In terms of like, let's say their magnitude, right? They have exactly the same magnitude. Well, which means then what I have here is, remember, we're given the charge and we're given the mass, and we're asking what is the magnitude and direction of the electric field. I know that in order for this housefly to levitate, the electric force has to be upward in order to cancel the gravity, right? So remember, so Fe minus Fg should be 0. So that's why Fe equals Fg. But then I can also need to find the magnitude and the direction. So I can find the magnitude by remembering that equation for the electric force is charge times electric field. So I replaced this with charge times electric field. An equation for the gravitational force is m times g. So this is mg. Then I can calculate electric field, which is mg divided by q. I have the mass, 12 times 10 to the negative 3 kilograms, times 9.8, divided by the q, which is my charge, 73 times 10 to the picostensor negative 12 coulomb. And then I can just basically do this calculation. All right, so an electric field would be, let's say in this case, 1.4 times 10 to the 6 Newton per coulomb. Okay. Now the question is that in which direction it is. Okay. Now, in terms of the direction, you have to kind of see if this is a positively charged, let's say our, housefly is our particle, right? If housefly is positively charged or negatively charged. Remember, if the test charge, right? If the test charge, and housefly in this case is the test charge, if it is positive, force and electric field would be in the same direction. And it is, right? Because what I have here is the housefly has a positive charge. That means the electric field will also be in the direction of the electric force. So it will be um, basically J hat. I can put it like that in terms of its direction. Now, in terms of could such a field exist in air? Well, this is about the field strength resulting in discharge through air. So it is unlikely the field would be strong enough to levitate the fly. So the field would be reduced by a discharge before reaching the strength necessary to levitate the fly. Okay. Let's look at another example here. 2-point charges are separated by a distance of 10 centimeters or 0.1 meters. One has a charge of negative 25 microcoulomb and the other plus 50 microcoulomb. Okay. So we just do the diagram here. You can see, right, you have two charges. I put Q1 negative 25 microcoulomb, Q2 plus 50 microcoulomb, and they are separated by a distance of 1 meter. Oh, sorry, 10 centimeters, so 0.1 meter. What we want to do here is we want to determine the direction and magnitude of the electric field at point P. We just choose some random P. Remember, when you're calculating electric field, you're just calculating effect of those source charges at some point P. There's nothing there for now. So that's why we have some point P between the two charges that is 2 centimeters from the negative charge. That means this point P over there. Now, it's important to understand that we have two source charges here. That means that point P will be affected by both of those. So there's going to be an electric field generated by the charge 1. Now, because the charge 1 is negative, electric field at the point P should be then pointing toward it. And that's what we have, right? This electric field over there, E1, is pointing toward Q1 because electric field of the negative source charge points toward the source charge. Q2 is positive, which means it also generates electric field at point P, but it is away from the source charge because positive source charge generates electric field away from the source charge. And that's this E2 over there. That means what we end up with is two electric fields, both of them pointing to the left. So then I can say, right, my net electric field is electric field 1 plus electric field 2, which means then I need to calculate the net electric field in terms of magnitude and direction, but so it's one dimensional, so it should be straightforward. So I can say E1 is K times Q1 divided by R1 square, and I can say the direction is negative I hat, plus K times Q2 divided by R2 square, that means this distance, right? And direction again is negative I hat. Then just basically add them together. I can see that I can do this. I can factor out K. So it becomes Q1 over R1 square minus, or I can just basically add them together, right? Q2 over R2 square and then do this minus I hat, right? Factor out I hat, negative I hat as well. And then just calculate. So 9 times 10 to the 9 for K. Then Q1, remember for electric field, using this equation, we're finding magnitude. So it has to be again absolute value. So 25 times 10 to the negative 6 coulomb divided by the distance R1. R1 here is, remember, it's 2 centimeters from the negative. So that means this is a 2 centimeter distance. So 0.02 has to be meters square plus then 50 times 10 to the negative 6 coulomb divided by then this distance, which is 0.08 centimeters square, then negative I hat. So then we can calculate then the magnitude of the electric field, net electric field, which ends up being 6.3 times 10 to the negative, 10 to the 8 Newton per Coulomb. That's our part A. All right, so that means at that point P right now, an electric field, and it is pointing in a negative I hat direction because this, I just carry this as well. So there's a net electric field to the left. Part B says if an electron that has a mass of 9.11 times 10 to the negative 31 kilogram is placed at rest at point P and then released, what will be its initial acceleration in terms of direction and magnitude? Well, let's see what we have. Well, I calculated the electric field, and in terms of acceleration, I have one equation, right? It's the force acting divided by the mass. Well, the force acting is going to be due to the electric field that is there already. That means it's basically Q times E. Remember, electric force is Q times E, then divided by the mass. Now, Q is my charge of the particle, and it's an electron. So negative 1.6 times 10 to the negative 19 Coulomb. And my electric field is then 6.3 times 10 to the 8 Newton per Coulomb to the left electric field, right? So negative 6.3 times 10 to the 8 Newton per Coulomb I had divided by the mass, 9.11 times 10 to the negative 31 kilograms. Then if I calculate, you can see, right, negative cancels negative, I can calculate, then I can get then the acceleration. Okay. So this is equals to 1.1 times 10 to the 20 meter per second square. And I hat direction gives me then I hat. That means what I have here is this. Remember, because the electric field is to the left, and because this is an electron, negative charge, the force at point P, when I put this charge over there, right, the force is going to be acting in the opposite direction of electric field, so it's going to be to the right. That means if the force is to the right, also is acceleration. So this charge, this electron, going to start accelerating to the right. Another very important thing I want to point out here is this. It says initial acceleration. Why does it say initial acceleration? Well, because this acceleration that I got, which is 1.1 times 10 to the 20 meter per second square, is not constant. Because see, when the charges, let's say, or let's say if I calculate another point P or something like that, right? So for example, if I calculate electric field at that point P prime, remember I'm going to get a different electric field. Electric field is P prime, triple prime, right? I'm going to get another electric field. And if this equation, right, it's Q times E, if my E is different, then F is different. Well, if my force is different, then acceleration is different. That means acceleration is not constant in this particular example. Well, if the acceleration is not constant, that means, we need to know some specific instant of time, right? What's the acceleration? That's why it says initial acceleration. The instant when the particle is right here at point P, because as it starts moving, force changes on it, acceleration changes, right? And we need to then calculate it again. All right. So again, so this is then an example in terms of when a charged particle is placed in an electric field, it experiences an electric force. If this is the only force on the particle, it must be the net force. Okay. Again, so let's say electric force, which is Q times E, and I just showed you, right? It also equals to then mass times acceleration. So I guess this slide would have been better if it was before this example. But the idea here is that it shows you that force, electric force, is just another force acting on any particle with mass. It's going to make it accelerate. The only difference here is, remember, this force is not a constant force, right? It changes with distance. That means two particles, if they have different distance with respect to one another, force is going to be different. So acceleration is going to be different. That means those kinematic equations that we used to have in mechanics, we can't really use them unless we know that the electric field is uniform and constant. If we know, if we're given that information that there's a region where there's electric field is constant and uniform, then we can actually use those kinematic equations. Otherwise, we cannot. All right, so here's one more example. So in this example, then we have, you can see, right, it says, figure below shows three particles with charges Q1 equals plus Q, Q2 equals negative two, sorry, Q1 equals positive 2Q, Q2 equals negative 2Q, and Q3 equals negative 4Q. And each has a distance d from the origin. What net electric field is produced at the origin? Again, now we have three source charges, and I want to know what is the electric field at that point P, which is happen to be then the origin. All right, so what I need to do here is, again, treat it like, the previous example, but then this is like two-dimensional. So I need to look at in terms of electric field due to charge 1. So here's charge 1, and it is positive. So then electric field will be radially away. So then this will be my E1. Okay, which will be 30 degrees below the x-axis, right? Pointing, in that fourth quadrant. Q2 is a negative charge, negative Q2, and it's going to have a force acting at that, electric field at point P, which is the origin, again, sort of like, let's say, based on the positive, negative source charge that we learned, right? But in this particular example, again, in the same direction, because the charge 2 here is negative, so it's going to be toward it. So, but again, it's going to be same direction. So I'll make it maybe a different color. All right, like this. So then this is E2. Okay. Now, why am I making them both same length? Well, because, so this is 2Q, this is negative 2Q, so they have basically same magnitude, and both of them have the same distance d with respect to that point. That means they are, producing same strength electric field, and even same direction, but same direction because of their specific configuration. Now, Q3 is a negative 4Q. Okay, so Q3 is a negative 4, which means it's a little bit stronger. And it is negative, means that there's an electric field toward Q3. So, okay. So it's going to be something, well, let me use a different color maybe. Okay. So it's going to be something like that. Okay. All right, so the reason I also have it longer because it is technically double the strength of E1 and E2. Again, how do I know that? Well, this is 4Q. Remember, electric field directly proportional to the charge. Okay. Now, then what I do here is I need to find the net electric field, which is electric field 1 plus electric field 2 plus electric field 3 to get the net electric field. All right. So here's one thing I can do over here. I can look at and say, all right, so electric field 1 is K times 2Q, right? Because that's K, KQ over R square, right? K times 2Q over D square. Now, what is my magnitude of electric field 2? Well, it's K 2Q, again, remember absolute value, right? Divided by D square. So technically they're the same. And look at it, in terms of both of them are also in the same direction. That means in a way, I can say I can just basically add a E1 plus E2 together directly because they're both pointing in the same direction. That means this is just K2Q over D square plus K2Q over D square. Let's say, let me put like R hat in terms of their direction, right? But at least, I can add their magnitudes because they're in the same direction. They're on the same axis and same direction. So this combination of E1 and E2, E1 plus E2, actually gives me K4Q over D square. Let's say K4Q over D square. That means I can come back and replace those two with one vector that has K times 4Q over D square. All right, so that will be something like this right now. Why am I doing that? Well, so that more or less I can show you that look at what I had for E1, E2, and now I have some of E1 and E2. Now let's see what I have for E3. In terms of its magnitude, it's K times 4Q over then D squared. See, this is K 4Q over D squared. And this one, right, this combined 1 and 2 is also K 4Q D squared. And both have the 30 degrees. So in a way, they're exactly same vector. One is, first quadrant, the other one is in a, you know, uh, first quadrant and fourth quadrant. That means what I can do here is like if I, so like let's say put it in a table like this. These are forces, these are my X components, my Y components. I could just put everything together, right? But I just wanted to show you that sometimes you can just do something like that as well. So here's my E3 and here's my E1 plus E2 combination. So this one here is, you can see that it's let's say E3 cosine theta. This one E3 sine theta. This one I'm gonna just say, like, let's say E net, E prime. Let me do E prime. So let's say I say E1 plus E2 is E prime. So E prime cosine theta, E prime sine of theta. But this is gonna be then negative because it's in a fourth quadrant, right? This is then the net force. Sorry, not net electric field. This is net electric field in the X direction, net electric field in the Y direction. Then if I'm looking at equation 1, which describes this column, and then net electric field in X direction is equals to E3 cosine of theta plus E prime cosine of theta. Well, E3 is K 4Q over D squared cosine of 30 plus E prime is also K 4Q over D squared cosine of 30. So basically I get, two of that. So I get, so K 8Q over D squared cosine of 30. Now, if I do equation 2, which is electric field in the Y direction net, so it becomes E3 sine of theta minus E prime sine of theta. You can see, right, E3 and E prime are the same. So this is my E prime, and this is my E3. They're the same. Thetas are the same. So this should sum up to 0. Okay. That means what I have here is, since my electric field has only horizontal component, then I can just use this, right? Plug in and, calculate, let's say, what I have as a total value for the net electric field. Okay. That means, kind of like right over here. So the net electric field is equals to K8Q over D squared. Okay. And cosine of 30. And if I kind of, plug in and let's say in terms of what is cosine of 30, right? And also, in terms of like the, I guess, either other values, right? So I can just basically find it. But at this point, I can just basically leave it like this. The rest is just basically simple calculations. But the idea here is that even if it's electric field, you have to treat it like vectors. You have to calculate the net electric field in terms of vectors, break them down components and things like that. And not forget in terms of the, let's say, direction coordinates, right, in, let's say, quadrants, right, and make sure that if it's negative in the angle, right, or the direction if it's negative, just include all of that, because these are vectors and you need to treat them as vectors, even though technically it's not a force, right? But you should see that it's pretty much identical to the net force calculation. It's just electric field. All right, so the next here is what we can do in terms of those electric fields. We can make the diagram look a little bit simpler for us by drawing what we call electric field lines. So field lines, you can see, right, are not the same as the electric fields. So electric field lines give us a means of representing the electric field, in terms of pictures, like pictorially. So then the electric field vector is always going to be then tangent to the electric field line that we're going to be drawing. Okay. The line has a direction that is the same as the, electric field vector, and number of lines per unit area through a surface perpendicular to the line is proportional to the magnitude of the electric field in that region. That means closer the field lines, stronger the field. So here's then an example. Let me actually do an example here for, let's say, for a point charge. So let's say here's a point charge. I know at this point P, there's an electric field right there. At this point P, there's an electric field like that. I'm radially away. Here, electric field like this. But if I come back here, see, this is the same radial line. There's going to be electric field like that. Weaker, but there's going to be electric field. Here, weaker, but there's electric field in the same direction. So we can just connect them together, and this is a field line now. This is a field line. This is a field line, right? So that means field line is just a line like that. So you can see, right, closer those lines to one another, stronger the field, further they are, weaker the field, which kind of matches that also the calculation of the electric field magnitude, which depends on r square, 1 over r square. All right, so let's say then what we have here is those lines represent, there's some kind of, maybe some kind of source here, and the electric field basically generated by that source. Okay, so we can see that the electric field line is kind of moving like that. And if I want to find the electric field at this point, I'll just do a tangent. So this is electric field at that, at that point. Electric field here, again, tangent, right? And so on and so forth. So we can always do that and find the electric field in terms of the tangent to the field lines. Okay. All right. So here's an image that I just, and drew those, in terms of positive charge, has all the electric field lines radially away. And it's a three-dimensional, not two-dimensional. That means, it's also moving toward us or into the page, right? So basically, it's a three-dimensional electric field. You can imagine then the positive, the negative source charge will have the electric field then going into the negative source charge. And the electric fields always start at positive and always terminate at negative. So technically it starts here and goes all the way to infinity. For the negative, it starts from infinity, comes and terminates at the negative. Right there. So it comes in and terminates here at the negative source charge. So that means you have positive, you have negative, which again you could easily see if I go back to the simulation right here, right? So see, like let's say I have those those are electric field lines, but if you kind of see the overall direction, you can draw lines, right? So you can say that these are then the field lines. These are the field lines. So let's say these are the field lines. Like that. It's not steady, but what I'm doing, but good enough, let's say. Right there. So those are, in terms of what we have. Now, another interesting thing here is this. So let's say this is the field line. Let me do that again. So this is the field line for the positive. This is the field line for the negative. See, it goes and terminates at the negative. What if let's say I have this negative over here, then I bring and put another positive over there. Then see, right away, all those electric field lines are affected by this, this configuration. That means what you have here is you have now electric field that starts from positive that used to then go all the way to infinity. Now they kind of change and go like this and terminate um, at the negative. Start from positive, terminate at the negative. Start from positive, terminate at the negative. Go like this. And this is something that we're going to be actually doing an experiment and looking at this. So this is actually called electric dipole. Positive, negative charges, some finite distance between them, and they have the same magnitude but different polarity. And you pretty much get this type of configuration like that. All right, so I have it here as well. So rules for drawing electric field lines for any charge distribution are as follows. The lines must begin at the positive charge and terminate on the negative. In the case of an excess of a one-type charge, some lines will begin or end infinitely far away. The number of lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. No two fields can cross. Okay. So this is what I had for the electric dipole. So you can see, right? So the starts from positive, goes to negative, and then electric field, always you can look at in terms of here's a tangent to that. Here's a tangent to that, right? That's the electric field. This is the electric field at that point P, which is actually then going to be superposition of electric field generated by both positive and negative charges. Okay. Here's what you get if you have positive, positive. So kind of like a region where there's no lines over there, right? And we can also have some kind of configuration. So plus Q stronger, minus Q weaker, and you can see, right, the region dominated by sort of like a positive source charge. All right. So then let's look at an example here. Imagine then going forward, we can more or less do the electric field lines. Think like this. Now what we have here is an example that gives us, in terms of an electron that is released from rest in a weak electric field, and there's a weak electric field. That's important, term. So weak electric field, what does it mean? So look at the value, negative 1.5 times 10 to the negative 10. Generally, electric field is in hundreds or thousands, and this is 10 to the negative 10. So it's a very weak electric field. And generally what happens here is when there's an electric field, then the particle can, has a force acting on it due to the electric field, but the electric field is going to be so small that if this object, even if it's an electron, will also be affected by the gravitational force, which is very tiny generally, but because of the very weak electric field, becomes significant. That means it's we have to take that into account as well. Also, one thing I want to point out here is this. I have another simulation that I want to show you. And this one basically goes like this. If there is a particle moving in a region, for example, and there's nothing there, just, imagine, let's say the gravitational force is, negligible here. You're just going to move, straight line like that. Okay. But then what we have, these two are like, let's say, a plates that we can assume that, let's say I can have this, one plate to be positively charged, another plate will be negatively charged. And if that's the case, then what I can have here is I can have then, let's say, reset this. If I have those plates, right? So imagine, let's say, if this becomes positively charged, and then this becomes, let's say, negatively charged. Remember what happens, right? Electric field goes from positive to negative. And then imagine that, let's say what I have here is this type of configuration. You have parallel plate and there's an electric field generated. Usually this electric field then becomes uniform and constant. So let's say one thing I can draw the electric field right now. So you can see, right, what I did, I assumed that there's no electric field, right? The plates were not charged and the particle just moved in a straight line. Now what I'm going to do, this one allows me to then increase the electric field. Now I'm going to say then, well, actually it's like this, right? From positive to negative. See, then stronger I put electric field magnitude, right? More lines you can see, right? Think like this. Now the idea here is that if you have a plate like this, then the electric field is generally uniform in this region, because the idea here is that the distance between the plates is too small compared to its length, so then the electric field is constant or uniform. But when the particle enters this region, then there could be a force acting on it because of the electric field there's there. And then let's see what happens with the particle now. See, as soon as it enters this region, it's no longer moving in a straight line, but there's a force acting now, in terms of, you can see, right? I'm given that my particle is 5 microcoulomb, which means my particle here is a positive particle, right? So you can see right here, 5 microcoulomb. And if it's a positive particle, then remember, force acting on it will be in the direction of the electric field. That means as soon as it enters here, there's a force acting on it, and this force makes it go down like this. Very similar to the projectile, right? Like a gravitational force, constant gravitational force acting on it. It goes in a projectile motion like that. That means what I have here is in this region where there's a uniform electric field, the particle then has a constant force acting on it, and it basically bends away, like, bends toward the, one of the plates. Now, one thing I can do here is this. What if I have negative charge rather than positive charge? That means I can just go this and make, like, let's say, negative charge. Let's see what happens when there's a negative charge entering the same region, same electric field direction. Well, look at what happens to the, let's say, negative charge. It is redirected in the opposite direction. Why? Because as soon as it enters in this region, there's a force in the opposite direction of electric field. That means now the force acting in this direction, and this force then makes the, it go and hit the top plate. Okay. That means the direction of the force depends on type of test particle I have. Positive test particle gives you the force in the direction of electric field. Negative test particle gives you the force in the opposite direction of electric field. And this is what we get. All right. So that means right now, if I go back to this example, I have this. So I have an electron released from rest in a weak electric field, and it has an electric field of negative 1.5 times 10 to the negative 10 Newton per Coulomb. It's in a J-head direction. That means basically there's an electric field in this region. There is like this, straight down. Let's say this region has an electric field like that. Okay. Let me do actually, like, let's say, so like a field lines. Okay. That means this is electric field in this region, negative J hat. Now it says you place an electron over there. Well, I take and I place an electron over there. What I have here is this electron has a mass. So there's a gravitational force acting on it, straight down. Because let's say, assuming that this is Earth. But there's also electric force because there's electric field. Now the question is, in which direction is the electric field? Electric force. Think about it. In which direction will be the electric force? Well, this is an electron. So electric force should be in the opposite direction, which will be in this direction. Then it says after the electron has traveled a vertical distance of 1 micrometer, that means it goes from this initial position to some final position, what would be its speed? It says, again, do not neglect the gravitational force. That means we assume that we put the electron there and let go, release from rest, right? And it's going to then, be pushed upward, because we can calculate electric force, separate from the gravitational force, and see that electric force technically is stronger. But, let's, trust me here. So Fe minus then Fg equals then mass times acceleration. Upward force, electric force; downward force, gravitational force. Their difference gives you mass times acceleration. Now, in order for me to get the speed, I need to know what the acceleration is. That's why I use this equation. So call this equation 1. Equation 1 can then give me acceleration, which is f of e minus f of g divided by m. F of e is then q times e minus m times g, right? Then divided by the mass. So then technically acceleration equals q times e over m minus g. Because if I separate them, right, mg over m just give you g. So this is my acceleration. The thing is, because look at the distance it's traveling, micrometer, just millionth of a centimeter, millionth of a meter, sorry. Which means that because then that electric field is so weak, we can assume that the gravitational force is already constant. That means for that small region, electric force will also be constant. So the acceleration is constant. Then here I can use kinematic equations. I'm giving my displacement, I'm giving initial velocity, then I have the acceleration. How do I then calculate the final velocity? Well, using equation 3 of the kinematic equations. Final velocity square equals initial velocity square plus 2 times acceleration times delta y. This guy here is 0. So then final velocity equals then square root of 2 times, then I plug in q times e over m minus g. So, and then do the calculation. All I have to do is just basically plug in all the values, and then I can see that in terms of my electric field, since my charge is negative and electric field are negative, they cancel out each other, and I can just calculate in terms of what I get for the, let's say, um, final velocity. Okay, so plug in everything, and sorry guys, I forgot here is delta y there. So plug in everything, and we should get 5.8 millimeters per second. I trust you should be able to just plug in everything and calculate that value. All right.